Okay, nice to meet you. So yeah, then we probably can start. Thanks everyone, thanks for coming. And today, next 30 minutes, we're going to talk about quite interesting, at least for me, topic. Not sure about how many of you are actually into databases, but for me it's super exciting. It's about how to run Postgres. And in fact, it happened to be that it's not that much of a Postgres specific here, so we can say how to run any particular database in Kubernetes. And yeah, a little bit of background. So my name is Dmitry, I work for Zalando, and me and my team, we basically run all the databases, all the PostgreSQL database in the team, in the company, in Zalando, and it's a lot of them, unfortunately. It counts already few. Oh, that's interesting. Perfect. We cannot see anything here. Okay. In the meantime, we can pay attention to this side. So yeah, as I said before, we run a lot of PostgreSQL databases, and what we're doing approximately looks like, I have to turn it on too, looks like that. So yeah. Basically, it happened to be because of different historical reasons that we have to run PostgreSQL in many different environments. So it's like just all data centers, just plain AWS environment, plain AWS cloud, and of course on top of Kubernetes. That's what we're going to concentrate on this right now. We're doing this thanks to two open source projects. You probably heard about them before. It's Patroni and Postgres Operator. Operator, in fact, is basically our Kubernetes operator to manage all this stuff. And when we're talking about running database and in fact any stateful application on top of Kubernetes, people are usually concerned about two facts, two problems. It's high availability and performance. In this particular talk, we're going to talk only about the performance aspect, because we already did me and my colleagues did a lot of presentations, and you can find them on the internet about high availability and how we're doing this, about Patroni and Operator. For example, last year in KubeCon, North America, and this year we're going to give a talk about this stuff on PGConf Europe. So yeah, if you're interested about this, you can go internet and check this out. We're going to concentrate on the performance side. For me, when I joined Zalando, and I was totally new about this Kubernetes, containers, and all this stuff, for me it was totally not clear how this resource isolation works. So I was trying to make some sort of like a journey for myself to figure out how does it work eventually, and what does it mean for PostgreSQL in particular. So basically the whole idea behind this presentation is simple. Whether or not, it's basically a simple question, whether or not we can get a predictable performance from PostgreSQL running on top of Kubernetes. So basically what we want to do, we will try to answer what are those magical incantations in our manifest means for our PostgreSQL, and how does it work on like a low level, how those thingies are really imposed on our applications, and what does it mean, whether they are good or not, and what kind of predictions for performance we can get. So we can start from the very, very background, from the really nothing. We have Kubernetes, we have Kubernetes node, and already at this point we have to stop a little bit, because at this point we already do not allow to consume all the resources of this Kubernetes node, because we already have something called Kubernetes allocable, which means that when we run, for example, PostgreSQL and this stuff, ideally when we have, for example, 16 virtual cores, well, there is no pointer here, unfortunately, but when we have 16 virtual cores, out of which 200 millicores are actually already reserved by Kubernetes and not available for us, unfortunately, which is already, well, in fact, it's not that big. It's like, just 200 millicores, who cares? But then it turns out, and I was thinking actually in the very same way, and then it turns out that things are actually a little bit more complicated, because obviously not only we have to just start Kubernetes node, we have to also run a lot of Kubernetes daemons and, Kubernetes appliance in general. And for me, it was totally surprising as, databases person, it was totally surprising that this appliance comes really not for free and sometimes consume a lot of resources. For example, we figured out that we can't really, for example, on node with 4 core virtual core, we cannot, for example, request more than like 3 and something core. And then even when we have, for example, R5 instance on AWS, which is like 32 gigabytes of memory, maximum that we can allocate, maximum that we can ask for Kubernetes is like 28, 30 maybe gigabytes, and everything else comes just to run Kubernetes. So, which is, well, questionable. And in general, I have to make a disclaimer. The whole idea about running PostgreSQL and database on top of Kubernetes is still questionable, but we can confirm that it makes sense. Sometimes it's really convenient. That's why we're going in all the way down to figure out how does it work. Okay, now we realized that we already have some limitations in terms of running stuff on the nodes. Okay, but now we want to figure out what does it mean for PostgreSQL to be running inside the pod, inside this Kubernetes node. So obviously, as you're aware, pods are basically Docker containers. So what does it mean to run something inside, well, especially in particularly PostgreSQL application, PostgreSQL database inside container? If you're curious, you can go to lib container specification. There you can read a really nice full explanation. What does it mean? What specify actually containers? So here we're going to go through quickly a bit. The most important part, and basically most of the time we're going to talk about this part, is about C groups, control groups. For those of you who are not aware, it's basically a mechanism in Linux kernel that allows us to limit resources. Well, in our case, limit PostgreSQL resources, limit those resources that Postgres can actually consume. The second really important part is namespaces. Basically, because all the applications that are living inside container, they should not be able to see other applications outside of this container. The third one is capabilities. It's also a Linux mechanism that basically says what kind of activity, what kind of permissions your application within this container are allowed to perform. And the fourth one is just a root file system. Before, in old days, it was like just a root. Nowadays, it's pivot root. It's basically which root file system you're going to use. So yeah, as you may see, it's basically 4 pillars. But for our presentation right now, what's important is the first one, C groups. And when we're talking about in general, when we're running PostgreSQL on top of some Kubernetes node, and we're thinking, we want to limit somehow, for example, resources of this particular PostgreSQL because we want to run also some other application on the very same node for work and survey purposes. So when we're thinking in this way, we have 3 dimensions. How can we do this? So first of all, we have to figure out what kind of resources can we actually isolate. Well, it happens to be that not all resources could be isolated. Actually, for example, kernel lock-in mechanism, few attacks are per CPU, not per C groups and stuff. So it's a little bit, they're kind of a global in this stuff, so we have no idea how to isolate them and so on. The second dimension is what kind of limits can we apply? Because limits also could be different. It could be like, for example, we can say, please give me a share of this CPU or this resource in general, like equal share, like fair share. Or we can say, for example, give me some limited amount of this resource. And we can say, for example, that we can do this strict limit or non-strict limit. It's also different. And the third dimension is time, because it's also important. It happened to be that via C groups we cannot limit some resource immediately. Basically, how does it work? Is we're doing some accounting, we're doing some job, and by results of this accounting, we apply some limitations. For example, throttle something. So the first we're performing some job, and then we're doing some throttling. And when we're talking about container, C group, basically container happens to be on the intersection of all those 3 dimensions. What I mean here is basically we have 11 controllers and 11 C groups that we can use to isolate our resources, not everything in our system, just 11 controllers. We can limit our resources in a different certain ways. For example, we can for CPUs say, please give me a share or limit. For memory, for example, it's even more interesting because for memory, it's basically a best effort. So there could be oscillations on this boundary. And like I said before, time, we cannot imply those limitations immediately, instantly. There is always some time gap. Well, basically, when we're doing a little bit more and then after which we're going to be limited. Okay, that was an interesting excursus to explain how does it work. But then when we're returning to our infrastructure world, it somehow happened that, well, it's not that straightforward to use those C groups even. Normally, when we're talking about C groups, the first thing that comes into mind is probably Docker, because it's most popular instrument to create those containers, those C groups with all this stuff that we were mentioning before. But then it's not the only one. For example, RKT, it's also quite popular. And as far as I remember, when the last time I've seen, there were questions about maintainability, but like 15% or so was running on RKT containers. There are also Linux LXC containers. There's also popular Podman. It's popular because it's, if I remember correctly, it allows us to run not only C group versions 1 containers, it allows us to run also C groups version 2 containers, which is really cool. And since we're talking here about this stuff, C group version 1 versus version 2, it's also quite hot topic. I just recently learned about this, that, yeah, basically, I mean, you're probably aware about these different versions. C group version 1 is kind of a legacy already, and by Linux developers it's considered to be a legacy stuff, but then somehow it happened that all the Docker and all the Kubernetes is run on top of this kind of a legacy system, and yeah, it works, please do not touch us. But then nowadays all the new stuff, for example BPF or fancy accounting, comes only to version 2, and not that many systems unfortunately using it. So there is a clear tension, no idea how is it going to be resolved, but nevertheless, for our purposes right now we have to concentrate only on version 2. Oh, sorry, version 1. So again, we have to understand. We have version 2, C group version 1. What does it mean? As I said before, we have different controllers, basically what kind of resources we can isolate. It's a CPU controller, it's a memory controller, it's a block IO controller, and so on and so forth up to 11. On the very same level, we also see systemd. Well, if we run some operation system with systemd installed on it, because systemd also requests some slice, some C group for itself for maintaining and managing all those services it's supposed to maintain and run. Okay. So it's a kind of a global. Most of the time when you have any laptop or server, most of the time you see those kind of high-level C groups. But then what I want to understand you from this diagram is basically this resource limitation. It's not one container you have for your application. It's a huge hierarchy, unfortunately. And this hierarchy could be pretty complicated sometimes. So when we're talking, for example, about Kubernetes and we run Postgres on top of this stuff, eventually our application ends up in a really low level in this hierarchy. So first of all, we have a C group for the whole Kubernetes appliance there. Well, not appliance, for the whole Kubernetes stuff that runs there. Then we have one C group, again, resource limitations per class of service, so best efforts, guaranteed, burstable, and so on. Then, well, it may seem that we already came to our application, but no, not yet. We came only to the pod within which application is working, and then we have a special C group for post container, which basically represent our pod. And only then we have our C group that basically belongs directly to our application. So this is a huge hierarchy, and it's important just because of the, well, performance consideration and in general, because when we, for example, want to account something, for example, we want to say that this application consumed this amount of memory already, we have to account not only to this one C group, we have to account it also to all C groups that are kind of parents for this one. So we have to propagate it through the whole hierarchy. And then sometimes when, for example, I don't know, do some operations, we migrate pods and so on and so forth, it also happened that this hierarchy have to be also changed. And for example, application can migrate from one C group to another. It also implies some interesting consequences. Okay. Now we covered this stuff, we understand more or less how C groups are working. Please, all the questions after the presentation, because I don't want to be interrupted. Please just remember it. So yeah, now let's return to this magical manifest. So first of all, let's talk about CPU. We're saying that we want to request some amount of CPU and we want to have some limitation in terms of CPU. What does it mean? Internally, basically all this stuff map, not one-to-one, there is a linear dependency between those numbers, but requests CPU are mapped to CPU shares in C groups, and limits are mapped to CFS quota, common fair scheduler quotas, again in C groups. What does it mean? Let me show you a nice diagram. So for example, when we're using request, we're basically using CPU shares. And just from the name, you can realize that basically we're saying if we have, for example, this, and this diagram represents the whole CPU resources on our node, we're saying that we have two applications, there are two C groups, and if they have equal shares, it means that we're having basically, we're dividing the system equally between those applications. So we're saying they're getting equal fair share of this resource, which is nice. In fact, it's called work conserving approach. And for example, if I understand correctly, the whole Facebook is trying to encourage this approach because we don't have any idling resources and then so on and so forth. Sustainable way, really nice. But then let's return to our original question, whether or not we can get predictable performance for PostgreSQL. Let's imagine in C1 we're running some PostgreSQL stuff, and then let's imagine, I don't know, we're doing some compression because we have to manage a lot of JSON-B, and this JSON-B have to be compressed to a stable and so on, so we're doing something CPU intensive. And then, well, Kubernetes of course tries to do it nicely, but it could happen that at the very same node we schedule two more applications because it's allowed and it's supposed to be like that. And then what happens that if we're using request, it means that suddenly instead of a half available CPUs, we're getting also fair share, but now it's 1/4, which is of course twice less as it was before. And we ended up in these situations like some sort of on the fly. And from the PostgreSQL perspective, nothing changed. So PostgreSQL was not doing anything more or less. It basically was doing the very same job, and something from the outside world changed, and we started to do this stuff less, well, performant, because we started to be a little bit slower. So yeah, work on survey, but then we can't really predict what's going on inside in terms of performance. Exactly to solve this problem, there is another thing, common CFS quotas basically. And this, using this mechanism, we're saying, please give us some bandwidth of resource, or CPU in this case. Which means that we're basically, we're not allowed to go over this bandwidth. And normally if something, well, happened, I mean, normally it should not happen, but normally it's not always, you know, everywhere happens normally. It could happen that part of our nodes are idling in the sense because we're just limited too much. It's not work on serving, but at the same time, when we, for example, schedule 2 more applications, there nothing changed for our PostgreSQL, compressing some data into TOS table, because basically, as we had before some share, some limits, then we're continuing to have the very same amount of CPU, which is predictable, which is a little bit nicer. But again, every feature, every functionality, every approach have its own pros and cons, and in this case, kicks in this stuff about how instantly we can apply those limitations. So obviously it doesn't make sense to imply those throttling, those CPU limitations every moment. It's just not too performant. That's why normally it's basically done like within the batches, within the silos. And if you, for example, go to proxies kernel, you will see that there is a parameter called scheduler CFS bandwidth slides nanoseconds. It's basically tell you how often this accounting is happening. And what happens here is that basically we have, as always, balance. We can, for example, say this accounting, make it a little bit stricter, make it a little bit too often, which means that we can isolate our applications nicer. So they cannot, for example, perform short amount of work within a short amount of period, but higher than it's supposed to be. But at the same time, it means that we're going to imply more CPU, CPU-intensive computations to actually enforce this limit. Which means that we're spending more CPU to actually maintain all the structure, which is not nice. And other way around, we can say, please spend less CPU on ensuring this limit, but at the same time, we're okay with breaching this limit from time to time. And in general, quotas actually are imposing for latency-dependent application a little bit higher latency. So, for example, in Zalando, basically we disable CFS quotas for the whole clusters in general, and yeah, that's how we're doing this. Okay, now we realize how we can slice the CPUs. But then there is another interesting stuff. Basically, with Kubernetes, we can say, please give me the whole CPU. Why is it important? It's because with whole CPU, we're getting not only like computation power, we also get all the cache that belongs to the CPU. Last level cache, we're getting, well, basically every kind of cache, all the 3 levels. And it's really nice because, I mean, we're going to talk about this a little bit later, but it's sometimes makes a huge difference. And with Kubernetes, especially with the newest versions, I guess, starting from 1.15, we can say basically that for all the guaranteed quality of services pod, if we say, please give us a whole number of CPUs, so not like 150 millicores, doesn't make sense, but nevertheless. So if it's like a whole number, we're getting kind of a research CPU for application, which is nice. And yeah, it's enforced via, again, C groups. Basically, this mechanism uses this CPU set controller in C groups again. Okay, now we kind of understand how CPU limitations are working. Second aspect, really important aspect, is of course memory. In C groups, we can see that we have request and limits memory, and in C groups we also have soft memory limit and hard memory limit. And actually it was really funny, my first reaction for this stuff was that, yeah, probably they map 1-to-1 as before. But with Kubernetes you never know, and it happened to be that memory requests actually do not correspond directly to any C group configuration whatsoever. Basically Kubernetes used this parameter to calculate, first of all, quality of service, and it uses this to compute, for example, OM adjust to figure out how to handle out-of-memory situations. But then still limits memory, they correspond directly to the hard limit, and if we're going to go over this hard limit, we're going to be OM killed. So my idea was pretty interesting. I thought, okay, we don't have soft limit, which is nice. Because in Linux, when you're going over soft limit, you have to think about this and you have to start to reclaim memory. So we're saying it's like the first signal for us that we're out of memory, we have to do something, and the Linux kernel tries to reclaim memory. And if we don't have soft limit memory, then probably we're not going to have memory reclaim. Thought. That basically was that were my thoughts. And of course I was wrong, and to prove it I had to write, well, BPF program. And by the way, I mentioned, I think in my abstract, that sometimes to figure out this journey, what Kubernetes works, you have to use some different interesting tools like perf, or you have to write some BPF programs for tracing. So in this case, I wrote BPF program to figure out how often we're doing and how much memory do we reclaim. And just it happens to be that since PostgreSQL is memory intensive application, by default, when we're trying to schedule all this stuff in the memory, we're already quite close in the memory limit by default, just because we want to make it again work conservative and efficient, which means that we already have memory pressure just by default, and we're reclaiming memory quite often, in fact. And we've seen already that sometimes when, for example, database spot is overloaded, we're doing memory reclaim quite often. And for you to understand, memory reclaim basically means that for every memory operation, if you want to touch memory page or something, you have to also perform memory reclaim. So you have to look for, well, scanning happens before, but you have to basically look what kind of memory you can reuse and return to the system, which is, of course, performance overhead. What else should we know about memory management here? So first of all, as mentioned before, memory and management is best effort, unfortunately. So which means that basically there could be breaches of memory management, relatively short, they should be at least, but nevertheless, so there is kind of an oscillation. And sometimes it could be actually relatively big, well, depends on your particular situation. As I mentioned before, memory request does not correspond to anything in terms of C groups, it's just basically for quality of service on adjust. The second really mind-blowing stuff for me was that, well, in C groups, we have two different, not the controllers, but configuration. We can control kernel memory and we can control user space memory. And my idea was that they're separate. They're not related to each other, because it makes sense. Kernel itself is a separate system, and our user application has totally different memory access and so on. And then suddenly, while reading the kernel source code, I realized that kernel memory actually contributes to user space kernel memory limitation. So basically it's a part of it. So yeah, please do not be considered, for example, if you're doing a lot of I/O and if you're like, well, allocating some significant amount of memory for maintaining TCP and all these packages, well, sometimes it could contribute also a lot to your application limitations. As much as for CPU, we're accounting memory in batches, because it doesn't make sense to account every single page. It's just too much of an overhead. But unfortunately, in terms of, well, in comparison with CPU, there is no nice toggle that will say, yes, please do this a little less frequently or more frequently. Basically, we have to account only by 32 pages. It's like a hard-coded number so far. And, well, apparently it works okay. No one actually suggested to make it configurable. And the last part, it's kind of already PostgreSQL specific, because as I said before, PostgreSQL, it's a memory-intensive application, and most of the memory actually kept in shared memory to be able to share it between different processes. It's just how it works, and actually a lot of databases are doing the very same approach. But then it happened to be that every time when you're trying to update a page in the memory for shared buffers, it has to be duplicated. It has to be created basically a new shared page. And for application that does it, it's like totally not transparent. For application that does it, it's basically the very same memory. But under the hood, one page was duplicated, and this page was accounted against your C group, which means that now you're consuming a little bit more memory. Normally, it's not a problem, but sometimes, and I think we've seen similar situations when suddenly shared buffers, shared memory consumption like rises in like 2 or 3 times. And it just happened when there is actually a special kind of workload for database, but sometimes it could happen. Some clients are coming and suddenly started to change all the pages, just because whatever reason. It's not exactly a correct approach, but it happens sometimes from time to time, which means that you're duplicating instantly almost every page in your shared buffers, and now you're consuming a lot of memory without your PostgreSQL actually understanding that, which is not nice. You can even end up in a OOM situation. Okay, memory. But it turns out I've showed the full manifest before. It turns out that Kubernetes allows us to even manage huge pages, which is really nice. So we can say, please give us request huge pages 1 GB, 2 MB, and the same for limit. So for you to understand, we're talking here about classic huge pages, not transparent, because it's totally different story, and please disable it. But there are, of course, different catches. Huge pages, I will explain why they're important and why it's nice. But huge pages could not be isolated, for example, per container within your pods. So, for example, if you have a sidecar and you have some other application within your pod, you cannot isolate. They have to use the very same, well, not the very same, their accounting for huge pages is going to be the same. And of course, there is no like a soft limit or claim for huge pages because they're just bigger. And in general, memory management is getting a little bit more complicated, and it's a bit easier to get OM killed if you're using huge pages. But normally, if you're doing this carefully, it's okay. And why is it important? Here is an example. Just a quick experiment, just a PG benchmark against the very same PostgreSQL database, the very same setup, the very same data, with just one difference. We were using huge pages in the first example and without huge pages in the second example. And here we were, as I said before, we have to use these interesting tools like perf, and with perf we're recording right now how often we're doing transaction look-aside buffer misses for load and store. Because, yeah, that's basically a cache miss of some sort. And we see that when we're using huge pages, it's exactly mentioned in the Linux kernel documentation. We're doing less, almost 20% less load misses and 30% less store misses, because huge pages memory management is a little bit more straightforward and performant, and that's why for applications like Postgres it's important to have. And it's nice that Kubernetes actually supports that. Okay, if you basically could notice already that all this memory management and CPU management we were mentioning before, it's the very same for stateless applications too. What's missing, for example, something special for PostgreSQL? In fact, a lot of stuff is missing, unfortunately. For example, right now, since we're limited by C group version 1, we do not have any meanings to limit I/O. Or, for example, last level cache, or networking. And it happened to be that, for example, with PostgreSQL, it happened to be that normal traffic fights for the networking with, I don't know, backup and with replication. It's important, actually. And you could be surprised how actually important last level cache, because sometimes it happened that different applications doing different memory management, well, they have a different data access pattern, and they are basically evict last level cache over and over from each other, and they're fighting for it. And you may say that, well, okay, we cannot do anything about this. Well, actually we can, because there are such technologies like Intel Resource Director, for example, and such, that allow us to slice this last level cache between different applications, and we can use it really nicely. And we will not go into details about everything, just quickly about block I/O, because unfortunately sharing I/O, well, in this case disk, between different applications in Linux, it's like awful. And this is not my quote, it's a quote from this article. You can go read it. There is a link down there. And why is it awful? Well, first of all, there is not clear what units to use to actually figure out, to actually count this stuff, to actually count block I/O. And the second one is that when we're throttling something I/O related, most of the time we're actually putting some more pressure on another part of the system, memory or CPU or something else. So it's always like a, we have to find a balance, and it's not always that straightforward to what to do. As I said before, we're kind of limited. We can't really isolate block I/O per se on C group version 1. So the only thing we can do is a monitoring. What's important for PostgreSQL here is basically a write-back, because Linux kernel has its own operation system cache, and basically all the I/O for PostgreSQL is buffered, which means that it goes through this cache. Which means that memory and I/O relation is really important in the sense, and sometimes Linux kernel tries to synchronize this operation system cache with the storage. And of course that's an extra I/O, and we have to be aware about this. Fortunately, we can monitor this. There are some event in perf called write-back section. You can monitor this stuff really nicely. But sometimes it could be not enough. Sometimes Linux kernel even injects I/O delays when Linux kernel is not being able to keep up with huge amount of dirty pages your application is generating. And this kind of stuff is not that easy to monitor. That's why, again, I had to write BPF program to figure this out, how often we're doing this. It's just an example. Just some, again, PG benchmark. In this case, we were doing this 4 times. We're having this delay, but it's not that much. But you can imagine that on the servers with 100-something gigabytes of memory, you can, of course, get much worse situation. Yeah. So why is it so bad with version 1? Because it was designed mostly for direct I/O, and for buffered I/O it's not really suitable. And it happens to be that there is no way to establish different relationship between different controllers. And for write-back we have to somehow work together memory controller and block I/O controller, which means that basically we cannot do this, and all the accounting basically all the account goes to root files, root C group, and everything basically comes global, which is not nice. We can kind of alleviate the situation even without C groups, because nowadays we have several interesting I/O schedulers. And here's, for example, a nice diagram. How does it work? So before we had only this section on the left, just I/O scheduler, CFQ, Noop, and something. You can check it. Maybe you still have it. But nowadays we have these multi-queue schedulers. And the point is that with modern hardware that we're using, usually this hardware NVMe devices or something, they have several queues. And we already kind of can isolate different applications, different jobs, different processes by these queues because they're also working in parallel. And normally what happens, for example, when we have a Kuiper scheduler supports two different queues. It supports software queues and hardware queues. And then whenever something happened, whenever, for example, one application consumes too much of a I/O latency bandwidth or something, it tries to throttle this application by limiting this queue depth, which is, well, relatively nice, and we actually performed some first benchmarks on Kubernetes. It really works nice in a sense that it gives us a little bit more predictable latencies. And yeah, but still, it's not a C group, since in a sense we cannot isolate, for example, different containers in this way. There is no way to do this, unfortunately, but then we can measure, for example, what kind of noise from I/O operations do we have. And for that, again, I had to write a eBPF program that basically attached to every time when we submit I/O and we complete I/O. And then, based on the information we get at those 2 points, we can assemble how much actually our application had to wait while other applications were submitting their I/O queries. Yeah, and the last part is about version 2. In version 2, it happened to be that all this stuff was taken into account. Version 2 really works nicely, much nicely, in terms of combination between memory and I/O, and in terms of, in general, isolating I/O per se, which is really nice. It's really pity that it's not spread out yet. And here's one just example. It's not exactly yet in the Linux itself as a Linux Next tree. It's basically a patch that allows us doing really something mind-blowing. It introduced block I/O cost estimator. So now, I mean, you can imagine before we were doing this I/O scheduling, and all the information we had is basically just a system information, nothing extra, and we had to somehow manage those requests and so on and so forth. With this stuff, we can say that there is an I/O estimator. It says this query is usually taking longer than this one. Taking this information into account, please try to isolate this workload so it's not going to be, you know, it's not going to be, they're not going to fight for this I/O in the sense. And I mentioned before BPF many times. This patch assumes that you can write your BPF program to provide custom schedulers, which is even more mind-blowing. Just another example that BPF is kind of conquering the world, and for Kubernetes, it's getting more and more important. And I guess we're more or less out of time, so just to give you a quick summary, the question was simple: whether or not we can get predictable performance from PostgreSQL. The answer, yes or not, unfortunately. From our experience, all the stuff that we're doing that mostly relates to stateless parts like CPU, memory management, and so on works pretty much nice. So there could be some different situations when it's like not exactly nice, but we can avoid this. With I/O, normally it also works nice, but then you should be careful. And for example, you have to allocate different pods with different databases together on the very same node. But ideally, they should have a little bit different, or maybe the same data access patterns. It depends on for what you're preparing the stuff. So yeah, I must say honestly, we do not go like fully to this way. We do not like, for example, we're right now just spreading for high availability and stuff, just because for us so far all this stuff about IO works, but we're improving this stack too. So, and I guess that's it. I hope you have a lot of questions about it. Yeah, first of all, there was a person who wanted to ask some question in between. My man, there was a mic, I guess, here. Yeah, it works. Thank you.
Yeah, so you mentioned at the start you had 12 of something.
11 controllers.
11 controllers. And how does that correspond to the C groups?
Well, basically, C groups allows you to isolate everything that corresponds to this one of those controllers. So I don't remember all of them from my head. So there is one controller for isolating CPU resources, one controller to isolating memory resources, one freezer, PIDs resources, block IO, and network, for example, I didn't mention, but network is also important. There are 2 controllers for that, and yeah, you can basically check. If you're interested, there is a little bit outdated, but still valid information in, for example, Linux kernel document section. Yep, any other questions? Come on. I just, yep, please.
One, the BPF scripts, are they on GitHub?
They are on GitHub. In fact, I didn't mention, unfortunately, so we didn't have that much time, unfortunately, to talk about this stuff, but I have an extended talk called PostgreSQL Stay Curious when I'm explaining this in more detail, and yeah, all this stuff in the Kubernetes, in GitHub, and I can share a link in Twitter probably later.
And the second one, you mentioned about that performance is important for you, and you're working with AWS, right?
Yep.
Do you have problems? Do they have like dual core systems, and we have problems with like getting CPUs from different NUMA nodes and using the KPI link or stuff like that?
That's a good point. I was trying to investigate. Somehow it happened that normally, well, that's probably an advantage of having Kubernetes usually and microservices. Usually people are creating something that consumes not that much of a CPU, which means normally we're allocating nodes without NUMA whatsoever, so we do not suffer that much. But then, of course, there are, for example, M4, no, we're not talking about all generations, M5X large or something. They have usually 2 NUMA nodes, and I was trying to figure out how does it work. That's indeed a problem, could be because if you have 2 different nodes, node pools, and Postgres, for example, allocates memory in one, and then somehow it have to access it from the other node, and the problem is that there is no way to measure that whatsoever, because on AWS they somehow screw up the firmware, and it just does not show all this information. So here, unfortunately, we're kind of blind, and we're just trying to avoid this by checking some, some side measurement, some side events, or just, kind of blindly looking what's going on and so forth. So yeah, unfortunately, it's a problem here.
Thank you.
Yep. Any other? Yep, please.
How much or how do you see that the predictability has gone up in your environment? So I assume that you've started at the point where you have wide variance of performance even on similar systems. So how close to a predictable performance have you gone with these tunings so far?
Well, in fact, we've got a little bit lucky, let's say in this way, because we already had a lot of experience before migrating to Kubernetes. And in fact, when we came on Kubernetes, Postgres was already really nicely configured. So fortunately for us, there was no situations when, for example, Postgres was really oscillating in terms of performance. And for example, nowadays I'm doing benchmarks like TPCC or just pgbench. Usually we're getting for nicely configured Postgres just a flat line. But the point is that when we started doing these benchmarks, and for example, comparing with different alternatives, we see that yes, sometimes we can do better. For example, with the Skyper, I just changed the scheduler, and without any other configuration, I get latency much lower, visibly lower. So basically, we're fighting right now for predictability in a sense, predictability that we can, for example, plan it better. So not like we have already nodes that like suffering from the stuff, but for example, we can approximately calculate what kind of latency or, for example, throughput we can get if we'll put PostgreSQL inside this pod on this node in a Kubernetes. So yeah. In general, you can actually get the situations when your performance for Postgres is like oscillating madly, but normally it means that you configured your pod not nicely. For example, you can fit not enough shares of CPU or something, and we see the situation already. It's just like it's an interface problem in this sense. Yep, more questions? Okay, then I guess already out of time, right? So yeah, we can stop. If you're interested, you can catch me up later and we can talk. Thank you.